Sorry for the false start, Jamie. I'd get disqualified at the World Championships, wouldn't I, for something like that? So it's always a pleasure to come and speak at these events. It's a highlight of the year. It's even better when you come on and speak after Vin Paleri, who just gives the best talks. And doesn't he ask for money in such a delicate way? He sort of sneaks it under the radar. You'd never even know it was done, would you? I mean, it's fantastic. As you know, I've spoken previously about our research on immunotherapy, but what I want to do tonight, rather than dwell on immunotherapy, which continues to go from strength to strength and continues to be supported by projects from Oracle. Oracle kind enough very recently to support a really exciting project that I hope I'll get to tell you about in a year or two's time as we see the fruit of those labours come to be. But what I'd like to do tonight is to talk about our radiation research, because of course sitting in the MDT with Vin every week and hearing how he's pushing the boundaries, curing patients with surgical techniques and really just doing the most outstanding work. We mustn't forget the fact that, of course, radiation therapy is the other treatment that can cure patients with head and neck cancer. And so this is a picture of, I guess, the godfather, the great-grandfather, perhaps, of radiation oncology. So this is Wilhelm Röntgen, and this is a photograph taken in the 1890s. On the 8th of November, 1895, Wilhelm Röntgen took a photograph, in fact, the first ever X-ray picture of his wife's hand. She is famous for having said, "I have seen my own death," when she could see her own skeleton on this picture. And so that was the first description of radiation, of X-rays, and that was about exactly 114 years ago in a couple of weeks' time. Remarkably, in contrast to how we develop things for clinical trials nowadays, and there's an argument about this as to who first did this. Of course, there's an American in Chicago who claims that, well, he doesn't claim any longer because it was about 114 years ago, but there's an American who was claimed to have done the first treatment, and then there are Europeans. But within about a month or two, patients were being lain down on tables underneath X-ray tubes and irradiated for everything that people could think about. So skin infections, eczema, aching joints, cancer. It wasn't really discriminated in the way it was used, but people were being treated very, very quickly. And of course, as we began to develop treatment, you can see that the technology changed. Now, the pictures that I have possibly don't look as whizzy as the robots that Vin has been able to show you, but there's been a progression in the way that we have developed radiation machines that I think has really been remarkable and continues to change what we're capable of doing. And so I'd just like to talk to you a little bit about some work which will culminate in a description of the MR-Linac, which is a new machine that some of you may know about. But essentially the first uses of radiation were the sort of picture you can see up there on the top left-hand side of the screen. It's a patient on the table. You can see in the room there's no real door between the radiographers driving the machine and the patient on the table, and there was a big lump of radium sitting in that machine, and there was a little handle that the radiographers would go in and they'd crank it open. The patient would lie under the table, under the beam, and when we were first doing this, or when doctors were first doing this, they'd irradiate the patient until the skin started getting pink after about a week or so. So they give it a little bit every day, and when it got pink, they think, "Oh, that's cooked, that's enough." And that was about as far as dosimetry went. By the time I started training, those machines in the bottom left hand, which are cobalt machines, which contain a lump of cobalt, but now the advance is that you can stay outside the room and press the button and the shutter opens. You don't have to wind it by hand. And again, the patient would lie under the beam, and the machine could rotate around into different areas, delivering the beam from different directions to add up the dose and concentrate it in the tumour. But again, this was fairly archaic technology. But I still remember those machines. There was a machine like this at the Marsden Hospital as late as about the year 2000 when they decommissioned it. Now, in the top right-hand corner, you can see a more recent development. This was the linear accelerator. And this was a way, rather than taking a lump of radioactive metal and sticking it in a big lead box and lying a patient underneath it and opening a shutter, this was using X-rays generated by electricity. So essentially what you do is you accelerate an electron close to the speed of light, and you crash it into a brick wall in the form of the metal tungsten, and as it slows down very, very abruptly, it emits all that energy that it gained by being accelerated in the form of high energy X-ray beams, and you can use those and direct those at patients. And using linear accelerators, we were able to deliver very, very precise treatment. And of course, this is the sort of machine that was used as we began to develop technologies such as intensity modulated radiotherapy. Now, Chris Nutting is in the audience somewhere, I think, towards the back, and Chris is without doubt the best technical radiation oncologist for head and neck cancer in the country, one of the best in the world, and developed intensity modulated radiotherapy for patients with head and neck cancer, and published the seminal study on sparing of parotid glands. And I'm aware that there are some people in this room who were treated before those technologies became widespread and became standard, and are suffering the side effects of the treatment that we delivered back in those days. And now that treatment has been vastly improved and much reduced by that technology. In the bottom right-hand corner, there is a more modern linear accelerator, and you can see that there are some things sticking out at the side. Now, those are the technologies that allow us to take X-ray pictures during the treatment, and so this is image-guided radiotherapy using X-ray imaging. And so what we were able to do is to make sure that we were positioning the patient and positioning the target so that we were treating the tumour as closely as possible and avoiding normal tissue damage. And that again has been a major advance, and again we're grateful for support from Oracle in supporting the research that has been done around developing image-guided radiotherapy. And we've had Chris and I have had programmatic grant funding from Cancer Research UK also to support that work, but Oracle has been an integral part of that. So the next evolution of that has been the so-called MR-Linac machine. Now, this is the machine as it was being opened, and there's Prince William being probably bored to tears with a discussion about how electrons accelerate close to the speed of light and crash into a tungsten target, because we all give the same sort of talk, I'm afraid. But here you can see on the BBC News, Prince William was visiting the hospital, and here you can see the machine being opened for the first time. Now, shortly after this time, we were able to take the first ever MR picture in the United Kingdom on an MR-Linac. Now, an MR-Linac has got all the bells and whistles of a linear accelerator, all that electrons accelerating, crashing into targets, X-rays, etc. But inside the machine there is a fully functional state-of-the-art MR scanner as well. So we can take MRI pictures of patients being irradiated. It's unbelievable technology. So we thought, with such a whizzy piece of kit, what could we possibly take a picture of as our first example? And so here it is. Does anyone have a guess as to what that might be? Gin and tonic, I hear everything. It's the Professor of Radiation Oncology's lunch. A Snickers bar and a Satsuma. So there's a healthy message there and a not so healthy message. So that is the very first thing that we took a scan of. But look at the beautiful detail that you can get. And of course, what we now use it for is to take pictures of patients. And this is the website from the BBC that accompanied the 6 o'clock news item where Fergus Walsh came and filmed the first patient ever to be treated on MR-Linac in the United Kingdom. And there you can see the gentleman lying down on the machine. I'm sorry to say that first treatment was not a patient with head and neck cancer. This was prostate cancer, because that's actually a much easier form of treatment to deliver, and technically a little less challenging, no less problematic for the patients who receive that treatment, but something that we wanted to start with. I'm pleased to say that we're on the very threshold, probably next month, in delivering radiotherapy on the MR-Linac to the first patient with head and neck cancer in the United Kingdom, and probably one of the first 3 centres in the world to deliver treatment to patients with head and neck cancer. And again, that is research that has been aided enormously by research funding from Oracle. So here I want to recognise the work of Jennifer Kieselman, and there's a poster for Jennifer out in the hall, and I didn't see Jennifer here before the meeting. I hope she's in the back. If not, I'd like to recognise her success. She was recently awarded her PhD thesis, funded by Oracle Cancer Trust, for research. And what these two pictures show, they demonstrate a problem that we're going to have to solve if we're going to be able to use this machine to its utmost capabilities. So imagine you have a machine that allows you to take a scan of a picture every single day to see where all the bits of normal anatomy, and you can see there's a jawbone with a blue line around it, there are parotid glands either side with other blue lines around it on the left-hand side of the image. If you've got a machine that can take a picture and show you where those things are, and they can move from day to day, if you had to sit a doctor down and draw around them on every single slice of that scan, every single day, that would take, and we've timed it, it would take as long as about 90 minutes every day. In the meantime, the patient would still have to be lying on the machine waiting for us to be sure we got everything in the right spot to press the button to irradiate. But what we really would like to be able to do is to have machine technology, machine learning, where we could teach a computer to recognize those structures and automatically outline them. And that's what Jennifer's PhD has demonstrated, that for structures in the head and neck, we're able to do that with a high degree of accuracy within a few moments, which means that we can actually take the picture, redesign the radiotherapy plan, and if the tumour's moved a little bit, you can redesign the plan so that it hits the tumour as accurately as you'd want it to do every single day. You're not just guessing where the tumour is, you're treating it with millimetre precision every single day. And that is a fantastic advance. We're also learning that we can take pictures and we can take contours on a CT scan, and we can actually migrate them between days, so we can do what we call deformable image registration. And we can, if you don't want to do this every day, you can do it every few days, but you can automate the planning process. And again, this is the work of Bryan Hin, who's a PhD student working on our CRUK program grant, and that work that he's been doing has been empowered by the research funded by Oracle to provide us with the images that we've got. And what Bryan has been able to show is that he can further speed up and automate this process so that we can get close to, when we're using the MR-Linac, we'll be able to use that machine to its utmost capability to make sure that we treat the tumour and we minimise the radiation dose to normal structures. So I think there's a fantastic opportunity now for us to revolutionise the way we deliver radiation. We will cure more patients, we will cause less damage, and we will significantly improve outcomes for patients. So alongside our surgical colleagues, we're going to be pushing at the boundaries to make these treatments work better. So in the last part of the talk, I'm going to change gears, if I may, because the title is Celebrating Successes in Radiation, and the MR-Linac and the work funded by Oracle is a huge success. But I also want to recognise other work that's being funded by Oracle, which is looking at the use of drug treatments alongside radiation therapy. So again, I'm aware that there are people in the room who've been on the wrong end of that drug that's listed there on the screen, which is called cisplatin, which is a horrible drug. Cisplatin was discovered, it's called Peroni's salt. It was discovered in 1845, and it was a chemical curiosity. It was used in the dye industry and various other things. And then some people started mucking around in the 1960s, putting electric currents through bacterial colonies and bacterial flasks. I'm not entirely sure why they decided this was a good idea, but they thought it would be some interesting research. And this is what they're meant to look like. The pictures at the top, which is labelled A, is what the bacteria normally look like. But if you put electric current through these bacteria, what you ended up with was long strings of spaghetti where the bacteria were unable to divide themselves, and they just kept growing at the ends, but they couldn't divide into single-cell bacteria. And the guys who did this, and this is very, very smart work, that they actually worked out it was nothing to do with the electricity. It was the fact that they were using a platinum electrode to pass the electricity through the liquid. And so they then started playing around with salts, platinum salts, and one of them was this one over there, which is the Peroni's salt. And what they found out is that when they put platinum onto these bacteria, they did exactly the same. And that led very, very quickly to this drug called cisplatin, which was approved by the FDA within 13 years. And that's really rapid development and has been the mainstay of the treatment of patients with head and neck cancer in combination with radiation since that time. And indeed, from 2000 onwards, when there was a big meta-analysis that showed that it improved cure rates by up to 8 to 12%, it's been given to countless thousands of people around the world, and these people have been very damaged by the treatment, all given in a good cause to cure the disease, but with significant complications for the patient. And the analogy I like to use, because of course we're all about targeted therapy and laser-guided bombs and really precision medicine, this is a bit like a blunderbuss, platinum. It really carpet bombs the area and it causes enormous amounts of toxicity. So the concept that I want to introduce to you now is the concept of so-called synthetic lethality. And this is it's a stupid term. I don't even know why they called it synthetic lethality, but I'll tell you how it works and what the thought processes are behind it. So imagine you've got a normal cell that I put up there on the screen, and it's got a laser beam, or in this case an X-ray coming towards it. So this is radiation attacking a normal cell. That cell will sustain some damage from the radiation, and broadly speaking it has a number of ways that it can repair that damage, and I've summarized that very simply as A and B. And the beautiful talk given by Arturo earlier on is exactly this case. ATM is on one side, those of you who remember that pathway, and there is an exam at the end of this. ATM is on this side and ATR is on the other side. So A is ATM, for instance, B is ATR. But the normal cell can choose between those because it has a full complement of its DNA and it hasn't got mutations, and it can choose how to repair the damage and it survives. Now, cancer cells, very, very frequently, in fact more often than not, and head and neck cancer is probably the best example of this, one of the best examples of this, they will cause mutations in those repair pathways, and it's a deliberate ploy. They don't think about it, of course, but it's a deliberate ploy by the cancer cells because it allows them to run fast and loose with their DNA replication, and they can pick up mutations as they go. So they can get rid of A and they can survive, but they still need something to fix some damage when it's really bad damage, and that's pathway B. And you notice I've drawn B a little bit bigger here, so they really rely on B and they upregulate, to use the jargon, upregulate B. So when you hit them with the radiation, that cancer cell can still survive. Now imagine, as Arturo showed, we develop a drug. In this case, this is a B inhibitor. In this case, an ATR inhibitor, like he showed, the VX compound or the AZD6738. In this case, in the normal cell, you block it in B, but it will find a way round by repairing through A with the radiation, and the cell still survives. But you can see where this is going. If we use a B blocker and there is a cancer cell there and we irradiate it, it's lost A, you block B, it's snookered and it dies. And so we've been interested now for some time as to how this might happen, and drugs that could be used in order to achieve this. And so again, I want to show you some work from one of the postdocs who worked in the team and who was involved in the early development, looking at the effects of radiation with this drug ATR inhibition. And this is the work of Hind Hafsi, and I'd like to pay tribute to the Bender family, who kindly funded this research through Oracle Cancer Trust, and which has been instrumental in taking this drug into the clinic. And so on the top, you see some pictures there. So please take it from me that the one on the left-hand side, which is a little bit blurry and has got a blue blob on it, that's what normal looks like. And the green dots and the hazy green thing in the top, right-hand side, is not what not a normal cell should look like. This is a cancer cell, and this is DNA damage. Okay, and these are quantified here in this graph underneath, and the graph is complicated. And again, so the simple message taken from this is, if you take a cancer cell that has lost pathway A, and we know that this cancer cell has, because we've checked it in the lab, and you give it a B blocker, in this case it's the ATR inhibitor, and you combine it with radiation. And in this case what Hind did was she also used another drug which is called a DNA PK inhibitor, which blocks another. So imagine instead of AB, it's got A, B and C, and we've blocked A, has been genetically mutated, and we've given drugs against B and C, and we've given radiation. The height of that orange bar tells you the number of abnormal nuclei that we see, those wavy green things rather than the normal blue things. And for us, that's a very, very clear signal that we're killing cancer cells. But not only are we killing cancer cells, we're potentially killing them in a way that might be visible to the immune system. And I'll come back to that in a little while. So again, with work that has been sponsored and funded by Oracle, and again partly funded by CRUK, with a major contribution from Oracle for some of the lab analyses. This is the work of Magnus Dillon, and I'll show you a photograph of Magnus in a short while. This is looking at exactly that scenario. So these, instead of now single cells, these are blobs of cancer cells growing in culture dishes. So you can see on the left-hand side, no treatment. There's a big blob there containing probably something between 10 and 20,000 cancer cells probably. And as we go with the drug alone, radiation alone, you see they have very little effect. But if we give radiation plus the drug, so the B blocker, when pathway A has been mutated, you can see how effective this is in retarding the growth of those tumor cells. Now, I mentioned the fact that we were interested in the effects of these drugs on causing activation of the immune system. So I'm just going to show you some pretty pictures, and again, just talk you through some of the detail of this. So on the top panels, again, you've already got your eye in with these blue cells. Those are the nuclei, and underneath them, you've got some color-coded ones. Now, these look like something from the sky at night and the Patrick Moore satellite around a planet or something. But this is what's called a micronucleus, that is a bit of DNA that has fallen out of the main nucleus because we made double-stranded breaks in the DNA, and when the cell divided, it couldn't quite package that thing back in again because it fell off the end of a chromosome. Now, that thing floating around in the cytoplasm, so the bit outside the nucleus in the cell, is a red flag to the immune system. And the more of those micronuclei that we can generate in tumor cells, the more likely it is that our immune system or a patient's immune system will see the presence of the tumor, and it will raise a red flag. And in the bottom graph, what Magnus did using time-lapse microscopy was he measured the number of those micronuclei that accumulate over time. And you can see the axis at the bottom is the time, with a camera automatically taking pictures every hour or so, and this is the number of micronuclei that you can see. And the purple line indicates drug plus radiation. The blue line at the bottom is neither drug nor radiation, and the other two lines in the middle are just the drug on its own or the radiation on its own. So you can see that by combining these treatments, we get a super effect against the tumor, and we make lots of micronuclei. What does this do if you have a tumor? In this case, it's a tumor in a mouse, and you give the radiation and the drug together. So on the left-hand side, what you can see is that there's a graph depicting how many immune cells are present in the tumor. Those are called T cells, and those are the cells that can react against and kill tumor cells. And you can see that there are more of them, and the brown stain there is just an indication of those T cells permeating through the tumor. So we know if we give the drug and the radiation together, we can make more immune cells come into the tumor. And you can see this rather complicated bar chart on the right-hand side. This is an analysis that Magnus did, and there's a nice picture of Magnus is on the right, and that's Martin McLaughlin on the left. These are the two individuals in the lab who've led this research, and they're both fantastic scientists. You can see that the green line indicates the changes in gene expression that occur when you give the drug and the radiation together. And these genes are genes that get turned on when there's an immune response happening. And what you can see by this chart is that the immune system goes crazy when you give the drug and the radiation together, and you get potent activation of immune responses potentially against the tumor. Now, Mannu Patent is here in the room, and is at the back of the room, and has got some data out in the main hall. Mannu has taken this work further again with research that's being sponsored by Oracle, being funded by Oracle. And again, I don't think Bob and Jenny Howes are here, but I'd like to pay tribute to Bob and Jenny, who are helping at this and providing funding through Oracle for this. And what Mannu has done, and he'll no doubt chat to you at length because he loves NK cells, he'll tell you all about natural killer cells and how they can attack cancers. And we see these really as very, very powerful ways to attack head and neck cancers. And so again, what you can see in the pie chart on the top is if you give the drug and the radiation together, that red component of the pie chart indicates the number of NK cells, and you can see he's counted them all up. He spent many, many hours at something called a fax machine, and that's not for sending messages. He'll tell you all about the other sort of fax machine. It is an incredibly precise and detailed analysis of the immune cells within a tumour, and so Mannu has generated these data, and all those stars along the top indicate just what a good scientist he is. He's a 4-star scientist. So I want to close with some clinical experience that we have with this drug, because so far I've told you lots of things that sound very good, but of course what we're really interested in doing for Oracle and with Oracle is to make outcomes better for patients. And so in tandem with all of this work that I've shown you, we actually have been running a clinical trial where we've been giving this drug alongside to patients who have been receiving radiation therapy. Now, there are some concerns about giving a drug that blocks the way tumours repair and normal cells repair DNA damage, and so we've started with really very low doses of radiation. So along the right-hand side, you can see there 20 gray in 10 fractions. So again, some of you may know that a full dose of radiotherapy to cure a head and neck cancer is 70 gray in 35 fractions. So this is a low dose of radiation. But what we've done is we've given that dose of radiation to a patient who's been taking a tablet, which is a B blocker. In fact, it's the ATR inhibitor AZD6738 that Arturo spoke about. And we didn't rehearse this actually, that we were going to talk about the same thing. You can see in the left-hand side where the red arrow is, where the big tumour is. Now, this patient was unable to swallow, was hardly able to speak, and was really very, very unwell, and was not well enough for us to contemplate a full course of treatment. This gentleman was 81 years of age when he started this treatment. He received 2 weeks of radiation, took some tablets for 2 weeks, and we thought that the tumour might shrink, but we expected it to come back. There is the scan taken 9 months after treatment. I've seen this man within the last 2 months, 3.5 years after treatment, and he remains in complete remission. So we're very excited about that. And that's, of course, what we call an anecdote. But when you do it a second time, or you see it happen a second time, we call it a case series, because it sounds a bit posher that way. And so, again, we've seen the same thing with a slightly bigger dose of radiation, but we see the same thing happening. And I'm pleased to say, and again, research that has been supported by Oracle, that AstraZeneca has recently agreed to fund a randomized trial of this drug with radiation in patients with head and neck cancer, supported by the laboratory work and by the clinical work that we've been able to do, funded by CRUK and others, but major component of that has been Oracle's involvement. And again, you can see a patient who has derived benefit. This man is now at 6 months post-treatment, and again remains free of disease. So I'd just like to close, as all the other speakers have, by thanking Oracle, thanking you as donors to Oracle and supporters of Oracle for everything that you do for the Cancer Trust. And certainly it allows us to do what we want to do, which is make outcomes better for patients. Thank you.